Hello, in this lesson we're going to define the second derivative and see how we can use the second derivative to analyze properties of functions. In this first example we have the graph of a function f. Let's label that f. And we have a couple points labeled on the graph along with the tangent lines to the curve at those points. So let's think about these two questions. At any point where f prime is positive, the slope of the tangent line to f must be positive. Therefore, the function f must be what? And at any point where f prime is negative, the slope of the tangent line to f is negative. Therefore, the function f must be what? Well, first of all, remember that the slope of the tangent line to f is just another way of saying f prime of x. So if one is positive, the other must be positive. If one is negative, the other must be negative. And in our example, we have this point A, where the slope of the tangent line is positive, and if a tangent line has a positive slope, it means the line is increasing, and it also means that if we zoom in really close towards that point, the function is increasing. So we can say that the function f must be increasing. If the curve has a positive slope, we can conclude that the curve is increasing at that point where the slope is positive. Likewise, if the curve has a negative slope, then the curve is decreasing at that point. That's a really important connection to be able to make. We're going to be working with this more throughout this course. Anytime we can see that a function is increasing, we can conclude that its derivative is positive at that point or on that interval. And then if a function is decreasing, we can conclude that its derivative is negative at that point or on that interval where it's decreasing. So the sign of the slope, whether it's positive or negative, tells us whether the function is increasing or decreasing. This is a very important key concept to analyzing functions that we, again, will be working with throughout this course. If the slope is positive at a certain point, we know the function is increasing at that point. That's the key idea here. If a function is decreasing at a point, we know that its derivative f prime is negative at that point. Okay, so the sign of the slope, whether it's positive or negative, tells us whether the function is increasing or decreasing. But we can also gather some information about the magnitude of the slope. The magnitude of the slope means the size of the slope without regard to whether it's positive or negative. So you can think of that as the absolute value of the slope. The magnitude of the slope, or the absolute value of the slope, it tells us how rapidly the function is increasing or decreasing. So positive slope, the function is increasing. And if that positive slope has a really high value, we know the function is increasing very rapidly. If that positive slope is a number close to 0, we know that the function is increasing but not very rapidly. So the magnitude of the slope tells us how quickly the function is increasing or decreasing. Now, the slope in itself is a rate of change. It tells us how quickly the position of the point on the graph is changing. So the slope is a rate of change. If we want to describe how quickly the slope is changing, then we're talking about the slope of the slope. So remember, we have different words we can use. The slope of the slope. I could also say the derivative of the slope or the derivative of the derivative. And so when we want to talk about the rate of change of the rate of change, that is called the second derivative. So again, there's a number of ways we can describe this. We can call it the slope of the slope, the derivative of the derivative, the rate of change of the rate of change, or even mix up any of those words. But this idea of taking the derivative of the derivative is what we call the second derivative. And again, that's just going to tell us how quickly the first derivative is changing. So let's summarize the connection we just made between f prime and f. Let f be a function that is differentiable on the open interval from a to b. We've talked about this word differentiable before. Differentiable means the derivative exists. If f prime of x is greater than 0, that's another way of saying positive. If f prime of x is positive on an interval from a to b, then the function f is increasing on that interval. Okay, so if f prime is positive, f is increasing. We want to be able to make that connection there. If f prime is negative, then f is decreasing. Wherever f prime is negative, f is decreasing. Notice that here we are working with open intervals, so it's questionable what's happening right at the endpoints. Is the function f increasing at a? Is it increasing at b? Well, that's a little more unclear, so we're going to wait and talk more about that when we discuss differentiability in our next lesson. But for now, if you're not sure whether your interval should be inclusive of the endpoints or not, just check to see if the derivative is positive at the endpoint, or negative at the endpoint, or 0 at the endpoint, and that'll help you make your decision. In this example, we have the graph of f of x, and we're asked on which interval is f prime of x greater than 0. F prime of x greater than 0 means f prime is positive. F prime positive. But that also means f is increasing. We just made that connection a moment ago. If f prime is positive, then f is increasing. And since we have the graph of f, that's what we're looking for on the graph. Where is f increasing? So f is increasing here on this part of the graph right here, and then also right here. Okay, so on the interval from -2 to 0, and then from 2 until 3 if we just stop the graph at the end of our viewing window here. Should we include the endpoints? Well, at this endpoint, f prime of -2, the slope of the curve, or the slope of the tangent line, is 0. And 0 is not positive, so we're not going to say that f prime is increasing at that point. We're not going to include the endpoint there. Same thing up here. We could find the derivative. F prime of 0 equals 0 because the tangent line right at the peak on the graph right there is horizontal, so it has a slope of 0, which is not a positive number, so we're not going to say f is increasing at that point. Okay, and then the same thing here, open intervals. So looking at our answer choices, we would select A. The interval from -2 to 0. On that interval, f is increasing, therefore f prime is positive. Now on which interval is f prime less than 0? So negative. That's the same as asking where is f prime negative? And that's the same as asking where is f decreasing? So where is f decreasing? Well, f is decreasing on this part of the graph here, and then this part of the graph right here. So from -3 to -2, and then from 0 to 2. And here, the derivative is not negative, so we're not including that. Here, the derivative is not negative, we're not including that. And here the derivative is not negative, so we're not including that. Now at this other endpoint right here, the derivative is negative, right? It is negative, so we could include it there. I guess if I go back here, I could have said the same thing right here. The function f is increasing at this point, is still increasing. Well, I guess I would be assuming that the graph continues, and that's maybe not a fair assumption to make. So we are better off leaving it open because we don't really know for sure what happens beyond that. So let's just go with open. And the interval from -3 to -2 is not one of the answer choices, so we will go with C, the interval from 0 to 2. On the interval from 0 to 2, f is decreasing, therefore f prime is negative. At which of the points is f prime of x equal to 0? Well, we've seen that. It's equal to 0 right here, and then at the peak up here, and right here, because if we were to draw tangent lines at those points, our tangent lines would be horizontal and have a slope of 0. So we'll go with choice B there. So we've seen that the derivative of y equals f of x is also a function, right? We can write it y equals f prime of x. That is a function. Hence, we can find the derivative of it. If it's a function, we can take the derivative of it, potentially. And so how would we take the derivative of the derivative? Well, we can apply the same definition of derivative, but instead of applying it to the function f, we're now applying it to the function f prime. So you'll see in our definition that this, instead of being an f, is now an f prime here and here, because we are applying the limit definition of the derivative to the f prime function. And it's going to give us the second derivative. So this is new notation for us, f double prime. If we were to say this out loud, we would say f double prime. I don't know if that's hyphenated. F double prime means the second derivative of f, or the derivative of f, or the derivative of f prime of x. There's lots of ways we can say it. So here we have, to start out with, the definition of the derivative of f. So we've seen this limit definition before. We're applying it to the function f, and we get the function f prime. Right? When we apply the limit definition of derivative to f, we get f prime. If I apply the limit definition of f, or to f prime, I'm going to get f double prime, which we call the second derivative. If I apply the limit definition to the function f double prime, I'm going to get the third derivative. So we can just continue taking derivatives of these functions. Every time we take the derivative, we get a new function, and we can just keep taking the derivative of those new functions. So the sort of number derivative, right, this would be first derivative. I'm going to abbreviate. First derivative, second derivative, and so on. That's called the order of the derivative. So the third derivative would have order 3, or the fourth derivative would have order 4, and so on. We're really just going to focus on first and second derivatives in this course. But, you might see a question where you're asked to find a third derivative. And it just means that you need to take the derivative of the second derivative function. Now we've seen different notations that we can use for derivative. So now we have different notations we can use for second derivative, and third derivative, and fourth derivative, and so on. The two that we use in this course are Lagrange notation and Leibniz notation. So Lagrange notation is our f prime of x. That's a very simple notation to use. It's easy to say, it's easy to write. Everyone likes Lagrange notation. So if you want to have higher order derivatives, you just keep adding more prime symbols. But after the third derivative, typically we don't just keep tacking on extra prime symbols. This starts to look silly. So you can see here they've switched to Roman numerals, but it's also appropriate just to write the Arabic numeral. That would be the fourth derivative of f. So that does not mean f raised to the power 4. That means the fourth derivative. If I wanted the 10th derivative, I would put in parentheses 10 right there. Or you could use Roman numerals as well. So that's Lagrange notation. Then we have Leibniz notation, which is a little bit more difficult to understand. But remember, for the first derivative, Leibniz notation, dy dx, we can also write it like this, where we put the y in parentheses because that's the thing that we're taking the derivative of, is y here. So if I want the second derivative, what I'm going to do is d dx, and in parentheses, I put the thing that I want to take the derivative of. So if I want the second derivative, I want to take the derivative of the first derivative. And this is the first derivative, so now I get to move that down there. So d dx of y. Okay, that would mean the derivative of the first derivative. But now I'm getting into a lot of parentheses. I'm writing a lot of d's and dx's. So we have an abbreviated way of writing that. Notice that we have dd here. So when we abbreviate this notation, we write d squared y. And we just drop the parentheses on the y. Over, and then in the denominator, we've got dx dx. So again, just to abbreviate that, we're going to write dx squared, like so. So when you see this notation, and we will be using this notation for second derivative. When you see that notation, you want to recognize, oh, that just means the second derivative of y with respect to the variable x. And again, we could take the derivative of that to get the third derivative. So in the third derivative, those values change to 3's. The fourth derivative, they just change to 4's, and so on. Now, if you're looking at other resources, you might also encounter Euler's notation, where to increase the order of the derivative, we're just changing this number here. The x on the bottom indicates the independent variable, x, and then the f is the name of the function that you're taking the derivative of. And we have Newton's notation. Newton's notation where you just add another dot above the y to indicate the next order derivative. Let's talk about concavity. Now, concavity refers to the curvature of the curve. Is that curve opening upward, or is the curve opening downward, or maybe neither? In the case of a linear function has no curvature, right? It's a straight line, no curvature, so it's neither concave up nor concave down. We have in the first graph a curve that is opening upward, so we would say this is concave up. Think about it like a parabola opening up is concave up. In the center, we have a linear function, so that's neither concave up nor concave down. And in the third example, this curve is opening downward. Think of a parabola opening downward. This is concave down. But we're asked to describe the rate of increase for each of these functions because all three of them are increasing. They're all increasing, but they're increasing in different ways. They're increasing at different rates. Some of them are increasing more quickly, some of them are increasing more slowly, and some of them are increasing steadily. Okay, so for the first one, imagine if this was just the side of a hill and you were walking up. It's getting steeper and steeper and steeper as we go from left to right. So this one is increasing at an increasing rate. And in the middle, we're increasing at a steady rate, but we're going to say increasing at a constant rate. And then the last one, it's getting less steep as we go. So increasing at a decreasing rate. So there is a connection between the concavity of the graph and its rate of increase or rate of decrease, which we'll look at next. These three graphs are all decreasing, but again, they're decreasing at different rates. And we can see just by looking at the curvature and how if it's opening upward or downward. In the first graph, this is concave down. In the middle, it's neither. It's neither concave up nor concave down. And the last example, concave up. So in the first graph, if we were again walking now down the hill, right, it's getting steeper and steeper and steeper as we go. We're probably not walking at that point, we're sliding. But this is decreasing at an increasing rate. And it's concave down. If we back up, this was increasing at an increasing rate, but it was concave up. This one is also changing at an increasing rate, but it's concave down. So you have to consider both things. Is it increasing or decreasing? And then add an increasing rate or decreasing rate before you decide whether it's concave up or down. Or obviously, if you have the graph to look at, you're just looking at the curvature and trying to determine it that way. So in the middle, we are decreasing at a constant rate. And in the last example, decreasing at a decreasing rate. Now we want to try and figure out what concavity has to do with derivatives. Does it have anything to do with the first derivative? Does it have something to do with the second derivative? Because remember, the first derivative is the rate of change of the function f, and then the second derivative is the rate of change of the slope of the function f. So the first derivative tells us how quickly the position of the points are changing on f, and the second derivative tells us how quickly the slopes are changing. Okay, so here we have a function that is concave up. It looks like it's probably a parabola. And we're asked a question about the tangent lines. We have some points plotted and their tangent lines along with them. These tangent lines all lie where in relationship to the curve? Well, if you notice, all of these tangent lines are below the curve. No matter where I place a point on this graph, when I draw the tangent line, it's going to be below the curve. The y value on the tangent line is going to be below the y value of the original function. That always happens when your graph is concave up. And as we move from left to right, what can we say about the slopes of the tangent lines? Well, let's see if we can come up with a numerical estimate for these slopes. So I'm just going to trace over this first tangent line here. I'm going to make it a little bit longer. And then I'm going to just slide it over here onto a blank area of my grid. So I'm going to line it up with this upper left-hand corner of the uppermost square on my grid, and then try and figure out the slope. Okay, so it looks like for slope, if I'm starting at this point, I'm going down 2 and over 1.5. So down 2 and over 1.5. That's negative 2 over 3 over 2, which is negative 4 over 3, which is about negative 1.3. I don't need to be like perfect with this. It's just an approximation. So I'm going to say negative 1.3 there. All right, and then let's try and estimate this one as well. So I'm just draw that a little bit longer, and then I'm going to move it over. If you do this with the edge of a piece of paper, just kind of butt it up against the curve, or like take a Post-it note would be another good way to do this, and let the edge of your Post-it note or your piece of paper or even a ruler represent the tangent line. Then you can move it along the paper to get it into a position where it's easy to do rise over run and compute the slope. Just make sure you don't tilt it, because then you would be changing the slope. You need to keep it parallel if you're going to slide it around like this. So I'm just going to go back up to this corner in the upper left hand side, and it looks like I'm going, this time it looks like I'm going down 1 and over 2. Maybe not exactly, but really close. Down 1 and over 2. So we'll say the slope here is negative 0.5. Okay, and then by symmetry, this one looks like 0.5 and this one looks like 1.3. So I've got these values from left to right: negative 1.3, negative 0.5, 0.5, 1.3. Those values are getting bigger. They're increasing. So what can we say about the slopes of the tangent lines? They are increasing. And the slopes of the tangent lines, we can think of that as a function, and any function that's increasing, its derivative is positive. That was one of the key concepts we saw at the beginning of our notes today. Any function that's increasing, its derivative is positive. So right now I'm saying the slopes are increasing, and the slopes are f prime. So if the f prime values are increasing, that means the f double prime values are positive. I'm going to put a therefore in front of that. Therefore, f double prime positive. Or usually we write it like that, f double prime greater than 0. So if slopes are increasing, the second derivative is positive, and the graph of f is concave up. If f double prime is positive, The graph of f is concave up. That's the connection between concavity and the second derivative. Let's look at an example that's concave down. The tangent lines this time are all above the curve. And as we move from left to right, what can we say about the slopes of the tangent lines? So this looks like it was pretty much the same, maybe just a reflection of this graph here. So let's go with 1.3, 0.5, negative 0.5, negative 1.3. This time the slopes are getting smaller and smaller and smaller. They are decreasing. And any function that decreases, its derivative is negative. So therefore, f double prime is negative. If a function is decreasing, its derivative is negative. And we're saying the slopes are decreasing, and the slopes are f prime. The slopes are the f prime values. So we're saying the f prime values are decreasing, and that tells me that the f double prime values are negative. Now, it's certainly possible that you have a graph that's only concave up on a certain part of the graph, on a certain interval, and then maybe it changes and it's concave down, and then maybe it changes again and it's concave up, right? In these examples, our graph was just concave down the whole time or concave up the whole time. But that's not necessarily the case. And it's not always that easy to tell whether a graph is concave up or concave down at a certain point, especially if that little part of the graph is not very curvy, for lack of a better word. If it's almost linear, then it's hard to tell sometimes what the concavity is. It's very easy if I draw a graph like this to say, you know, what is the concavity on this interval right here, right? That's very clearly the curve is opening down, so it's concave down. That's easy to tell. But if I then said, well, what about at this point right here? Is it concave up or is it concave down? You might have a hard time deciding. Is it concave up or is it concave down? Because again, it's very clearly concave up down here. And if it was concave down in the yellow portion and then concave up on the green portion, somewhere it had to switch. Somewhere it changed from being concave down to concave up. Where did that happen? Did it happen where I drew that pink point? Or did it happen right here? Or did it happen right here? Or did it happen right here? Where did it change from being concave up to concave down? So it's not always that easy to tell. But my advice to you, let me get rid of some of these extra points here. Let's just say we're trying to figure it out right here. Like, is it still concave down there or is it concave up there? One thing you can do is draw a tangent line, and you know, maybe it'll be easy to tell which side of the curve the tangent line is on. Because if the tangent line is below the curve, you know that the curve is concave up there. So here I would say, yeah, concave up. The tangent line is below the curve. So if you have a ruler, or again, just a Post-it note or the edge of a piece of paper, slide it up against the curve at that point and ask yourself, is, you know, because the edge of that paper or that ruler represents the tangent line, is that below the curve or is it above the curve? You can also try, let's pick a, let me move that, pick like a different point. It's really hard to tell because on this whole portion of the graph right here, if we zoom in, it just sort of looks linear. So it's hard to say whether concave up or concave down, right? So hopefully you won't get a point where it's that hard to tell. It's much easier to tell right here because you can probably just visualize yourself drawing the tangent line. Or if I took a ruler or the edge of a piece of paper, this just represent the edge of the ruler or the piece of paper, then I would want to imagine sliding that around and seeing if it's above the curve or below the curve. So it's above the curve here, that means concave down. The curve is concave down at that point. So that would be how to use a tangent line, right? I'm just butting it up against the curve until it looks tangent. You can also try and do this by imagining a secant line. If you get a really tricky one, you're not sure if it's concave up or concave down. Go a little bit on either side of the point you're interested in, and then draw a line, a secant line through those 2 points. So for the secant line, if it's under the curve, concave down. Is the opposite of the tangent, right? Let me move the tangent line back over to that point. There's the tangent line. Oops, move it a little more. There we go. So the tangent line is above the curve, meaning concave down. The secant line is below the curve, meaning concave down, right? So it's the opposite conclusion there. So you can try using a secant line to help you figure it out, or you can try picturing a tangent line to help you figure it out. All right, the second derivative. Let f be a differentiable function on the interval from a to b. F is concave up on this interval from a to b if and only if f prime is increasing on this interval. Remember, again, we said if we have a function that's increasing, we know that its derivative is positive. So I'm going to just tack this on at the end here. And f double prime is positive. So f is concave up if and only if f prime is increasing, which is equivalent of saying f double prime is positive. If you can look at a graph and see that it's concave up, you can immediately conclude that f prime is increasing, and you can immediately conclude that f double prime is positive at that point where you're looking, at a point or on an interval. And then for concave down, f is concave down on an interval from a to b if and only if f prime is decreasing on that interval, which we could also conclude from that the second derivative is negative. So this works at a point or it works on an interval. We have a direct connection between concave down or concave up and the second derivative. If f is concave up, the second derivative is positive. If f is concave down, the second derivative is negative, and vice versa. Okay, for our last example here, we're going to try and sketch the graph of f prime and f double prime from the graph of f. So we're looking for key points first. I'm looking to see where does it look like the slope of f is 0. So if I imagine drawing tangent lines there, they look horizontal, so the slope is 0. So I'm going to now on my f prime graph plot the point with the same x-coordinate. So I'm just going to follow that x-coordinate down, but use a y-coordinate of 0. Let me write down my slopes here because that's what I'm plotting as my new y-coordinate. So I've got a point here and I've got a point here. Then let's go ahead and get this point in the center. And I'm going to imagine drawing a tangent line there. What is the slope of that line? It's about 1/2. Right? I don't know if it's exactly 1/2, but we just need to get close. It looks like I'm going about 1/2 there. So I'm going to plot a point, and there's no scale on the vertical axis, so I'm just making the decision 2, 3, 4 that the scale is 1 there. Okay, and then I also have the advantage of knowing that the function f is polynomial. I recognize that. I can see it looks like a degree 3 polynomial. And a degree 3 polynomial, when you take the derivative, is going to result in a degree 2 polynomial. So my derivative graph should look like a parabola. So I really already have the 3 points that I need to sketch the parabola. But let's do a couple more. So we'll just pick this point right here, draw a tangent line, estimate the slope. So that looks like it has a slope of maybe down 2/1, -2. So I'll follow that x-coordinate down and plot a point at -2. And then it looks like this point right here also has that same slope. It has a slope of about -2. So follow that down, -2. Okay, so I didn't get it perfectly because a parabola would be perfectly symmetric. And so this last point that I drew is off a tiny bit, but that's okay. Then we're going to connect those points to get our first derivative graph. Now, looking at the first derivative graph, let's think about what does its derivative look like. So again, I want to imagine some tangent lines. Right here at the peak, the slope would be 0. M equals 0. So same x-coordinate, we follow that down and plot a point where y equals 0. And then how about this point right here? That looks like it's up 1 over 1.5. So 1 over 1.5. 1 over 3/2 is 2/3. So that looks like it's m equals 2/3. And then this should be symmetric, so we're going to call that one negative 2/3. Okay, so follow the x-coordinate down, plot a point at 2/3. Over here, follow it down, plot a point at negative 2/3. And again, I know that if I take the derivative of a degree 2 polynomial, I'm going to get a degree 1 polynomial. And a degree 1 polynomial is a linear function. So my point is off a little bit. I know that's supposed to be linear. Or maybe I just didn't tilt it enough when I drew it. No, it's not. It's off a little bit. But that's okay. It's close. So this would be my f double prime graph. All right, that does it for this lesson on second derivative. Next time we're going to be talking more about continuity and differentiability. Thanks for joining.